Hello everyone, I'm Teng-Yok from Mitsubishi Electric. Today I will present DynamicsExplorer visual analytics for robot control tasks involving dynamics and LSTM-based control policies. The authors are from the Mitsubishi Electric Research Lab at the Ohio State University, including Wenbin He, Teng-Yok Lee, Jerome Van Baar, Kent Wittenberg, and Han-Wei Shen. In machine learning area, reinforcement learning is an active research topic to solve problems that are difficult to annotate. While reinforcement learning is very successful in virtual environment for chess planning and video games, researchers wish that it can be applied to solve real-world tasks like robot control. Figure below overview the basic idea to apply reinforcement learning for robot control. We first measure of the state of the robot to control, which can be 2D image or 3D point cloud. Then we forward the state through a machine learning model like a neural network to get action to control robot. Once the action is applied and the environment change, we compute reward function. This reward function is used to compute rows to train a machine learning model. A major issue to apply reinforcement learning is that the training can involve millions of iterations. It is very difficult to directly train on a real robot because robots are expensive and the operations can be very dangerous. As a result, it's common to first train a robot model with a simulator that mimics the robot and the environment, and later transfer the model to a real system. This process is called sim to real. Ideally, machine learning scientists wish to transfer the model from the simulator to a real environment without any extra steps. However, this is very difficult to achieve, especially when a task involves dynamics. In order to explain the idea about dynamics more concretely, here we will describe robot control task. In this task, scientists want to train a robot arm to play a maze game, as shown in the middle figure. This robot arm can rotate the axis clockwise and counterclockwise in a fixed angle, and vice versa for the y-axis. There is a ball in the maze, and the robot arm should control the maze to move the ball from the outermost ring to the center. The rightmost figure shows how the robot arm plays the ball. In this case, the dynamics essentially means the motion of the ball and the maze, which can be represented by the ball location and the maze tilt, the angle over time. They are related to various parameters, such as the friction of the maze surface and other mechanical parts inside the robot, and can be related to latency in the robot controller. Because of the dynamics, it brings several challenges to reinforcement learning, and especially sim to real. First, now the simulator needs to consider more physical equations and parameters, and unfortunately, some parameters in a real environment are difficult to measure, and so the simulator may use inappropriate parameters. Second, it also makes the underlying machine learning model more complicated. Because dynamics is time dependent, we often need temporal aware machine learning model like LSTM, which are still difficult to interpret. Because of this, it's usually difficult to transfer the model from the simulator to the real robot, and so extra training on a real robot is still needed. In other words, if reinforcement learning scientists want to achieve sim to real, they need to better understand how their reinforcement learning model reacts to the dynamics in the task they want to solve, and they need to understand how robust their model can be when the parameter changes. In this paper, we present a visual analytic tool called DynamicsExplorer to help reinforcement learning scientists to understand the impact and sensitivity of different dynamics-related parameters to their reinforcement learning model, and provide a guideline for the scientists to improve their model. This is the interface of DynamicsExplorer, which includes the following components. First, it shows the relationship between the dynamics-related parameters and the test result, so scientists can know which parameter or which combination of parameters can make the model to finish the task or fail. Second, it allows scientists to interactively explore the neural network activations to see how the internal activation changes with respect to the dynamics, and whether there exists any pattern. Third, it allows scientists to correlate the parameters and the neural network activation patterns, so they can form hypotheses about whether certain paths in the neural networks are responsible to certain behaviors. Scientists can also use DynamicsExplorer to verify their hypotheses from the multiple test results. This slide describes the pre-processing stage in order to apply DynamicsExplorer to diagnose a chain reinforcement learning model. Given a model to diagnose, the first stage is to test the model under different parameter settings. In the math task, the dynamics are related to the initial port location, the friction of the maze service, the latency of the robot controller, and so on. Given a combination of parameter values, we test the model to collect dynamics of the maze and the board over time and the corresponding neural network activations. This piece of information will be stored with the parameters to a disk. We repeat the process for all combinations of the parameters. Because the stage will generate lots of test results, the pre-processing includes one more stage to aggregate results, including clustering and dimension reduction. Later, DynamicsExplorer can utilize this aggregate information to interactively visualize and to explore the model. The first part of DynamicsExplorer is to help scientists to understand how the parameters can impact the final test result of the model. In reinforcement learning, a trial of the model is called as an episode. For instance, in the right, we show how the ball is played in the maze. Here, an episode starts when the ball is placed in the outermost ring of the maze, and it ends when the ball reaches a terminal in the center, or just timeout. In other words, we want to understand how different parameter settings can impact an episode. Given a combination of parameter values, did an episode successfully complete a task? Did it fail? Or did it take a much longer time than usual to complete a task? In other words, is there any correlation between the end result of the episodes and the parameters? As we have the episodes for various combinations of parameters, we need to summarize each episode into an effective representation for analysis and visualization. And our approach is to use the trajectory of the ball in the episode, as shown below. And given an episode, the trajectory essentially encodes the dynamics of the ball, and it's very easy to overview on a single image. Given the trajectories of all episodes, we apply hierarchical clustering to group episodes with similar trajectories. In each cluster, we use the trajectory that has smallest distance to the other in the cluster as its mean, and assign a unique color to each cluster. As the mean trajectory represents the dynamics behavior of all cluster members, by plotting the mean of all clusters on the maze, scientists can overview the representative trajectory from all episodes. For each cluster, we also show the overlapping area of all members as ROPs, as shown in the right. To show how the episode trajectories are correlated with the parameter settings, we use a pair coordinate plots where each axis represents a parameter, and then we plot the parameter setting of each episode as a point line on a pair coordinate plot. For the episode of the same cluster in the previous slide, we also group them on a pair coordinate plot. Then we use the brush linking to link the trajectory in the maze and the polylines on the pair coordinate, so scientists can interactively see how the trajectory are related to the parameters. Here we show how to use the DynamicsExplorer to locate abnormal cases and their relationship with the parameter settings. In the top, we choose a cluster in light green color. In this cluster, the ball cannot reach a terminal because the ball was stuck in same location. In the bottom, we choose another cluster of episodes in the purple color. While here, the ball can reach a terminal, their trajectories are longer than the others. Because the ball passed through a gate, we call such a phenomenon as overshooting. In the pair coordinate plots, we use the second axis from the left to show the friction value of the maze surface. In the top, we notice that these friction values are high. This means that the ball will be harder to move on the maze. In the bottom figure, we notice that the friction values of the overshooting episodes are lower than those in the top. In other words, the maze becomes leaner and thus harder to stop and to control the motion of the ball. While the scientists and we are not surprised that friction values are crucial, a bigger surprise is that these values are also related to initial ball location. If the ball is placed at different location, it can successfully reach the terminal, even if with the same friction value settings.
The second goal of DynamicsExplorer is to help scientists to understand the machine learning model, especially its relationship with the dynamics. As it's common to use neural networks nowadays as a machine learning model, scientists want to know whether there exists any pattern in the neural network activation. How is the activation change when the parameter change, especially when a test fails? Let's briefly overview the neural network for the math task, which is common for other reinforcement learning tasks with dynamics. In the neural network, the first part is composed of time-independent layers. This part is designed to illustrate the feature of individual time steps. The second part is designed to fuse the output of the first part over time. For this purpose, it's common to include recurrent layers like LSTM. In DynamicsExplorer, we will focus on the layer at a time-dependent part, especially the LSTM. This is because the dynamics is a time-dependent phenomenon. This is also based on the scientific previous study, which showed that the time-dependent part is harder to transfer to new environments. Let's briefly review how LSTM works. LSTM works by recursively fusing the current input, previous input, and an internal vector called hidden state over time. The hidden state is designed to encode temporal information, and this is what scientists want to understand. As the hidden state values are changed over time, by creating these time-varying vectors, we can form a 2D map, where the x-axis represents the time and the y-axis represents the hidden state element, which are typically called channels. However, the map itself will be difficult to understand. The reason is that in the hidden state vector, the order of the channels are arbitrary. Without any ordering, the map will seem random and difficult to find meaningful patterns. To solve this issue, here we treat the activation of each channel as a long vector and apply principal component analysis to project the channel-wise activation into a low-dimensional space. After the projection, we can find the most representative patterns within the LSTM layers.
In DynamicsExplorer, we provide a view for scientists to visualize and explore the activation of LSTM of an episode. In this view, the top shows the P map, which represents PCA of the activation map over time as an overview. The scientist can use the mouse to select a range of time steps of interest on the heat map. So when they adjust the time range, the corresponding point location are also highlighted in the maze view. The selected region of interest are enlarged in the bottom right with another heat map, so scientists can examine the activation patterns clearly. Beneath the enlarged heat map, we also show the maze tail angle and the point location for scientists to understand the status of the robot. On the other hand, even though we reduce the cluttering and highlight the salient pattern of the activation over time, it's still difficult to interpret given a single episode. As a result, DynamicsExplorer allows scientists to interactively select two episodes and to compare. For instance, if scientists want to analyze the activation pattern of an overshooting episode, they can select another normal episode that have similar trajectory before the overshooting. On both episodes, scientists can select a sub-episode to compare. In this case, they are the similar short trajectory just before the overshooting. Then, DynamicsExplorer will align the two selected sub-episodes based on the ball location and show the difference of the activation map after the alignment, as shown in the right. In this example, we can see that although the ball trajectory are similar, but inside the LSTM layer, the activations were already becoming different. Below the activation map, we overlap the maze tilt of the two sub-episodes after the alignment. This shows that the maze tilt angle started to diverge just before the activation pattern started to become different. For the comparison in the previous slide, scientists can know in the selected episode which time step and which channels are apparently different when the abnormal behavior happens. Now, scientists can form hypotheses about which channels are important, but to verify they have hypotheses, they need to confirm whether the same pattern also occurs in other episodes with similar behavior. To help scientists to confirm their hypothesis, DynamicsExplorer allows scientists to search activation patterns of interest in other episodes. First, scientists can move to select sub-episode in the top activation map over time. Next, scientists select a channel with this sub-episode by clicking on the corresponding row. Then, the scientists can click on a button of DynamicsExplorer to trigger it to search through all episodes in the database. The episode with match activation of the selected channel will be then shown in the right for scientists to examine. And here we show a live demo to use this feature to search the episodes. Here we briefly discuss the technical challenge to search the activation pattern of sub-episodes in other episodes. The main issues are that the pattern may appear arbitrary time steps and that the length can be different as well. If we just do brute force search, it will be slow to consider all scales and all locations. Dynamic time warping is often used to efficiently match time series, but is designed to compare anti-time series. To overcome this challenge, we use a modified pattern matching algorithm called sub-DW. With sub-DW, we can locate time series pattern in other time series, even though the pattern exists in different location and different scale, and the time complexity is still the same as a conventional DTW. With sub-DW, scientists can compare the matched episodes to understand more about the neural network. For instance, they want to know whether any channel in the LSTM are responsible for the overshooting. If such a channel exists, they will like to do more on these channels. For instance, here we show an episode with overshooting. We highlight the sub-episodes before overshooting happened and the channels with apparent difference from a normal episode. In the right, we show 3 episodes with more similar activation patterns of these channels. We highlight the matched sub-episode with a color code to indicate the action. Here we can see that those sub-episodes are just before the overshooting the same gate. This indicates that these channels are highly correlated with the overshooting behavior in this area. Here we show another application with DynamicsExplorer, which is to guide the scientist to fix the error model. Figure below shows 2 fail cases we discussed earlier. Based on DynamicsExplorer, we know that the failure cases are not only related to the maze friction, but also the initial ball location. Conventionally, if the scientists are not satisfied with their model, they will continue to train or fine-tune the model with more episodes. Because they don't know the relationship between episode result and the parameters, they will just randomly sample the parameter space, which can be huge and so slow to fine-tune the model. Now, as DynamicsExplorer indicates that the fail cases are correlated with a limited range of initial ball location, they only need to fine-tune from these locations. Figure below overviews the episodes after such a guided fine-tuning. With only 400 more episodes to train, the overshooting and stuck phenomena were gone. On the other hand, if we still do random sampling, we found that the fine-tuning needs 10,000 more episodes to fix the issue, which are much longer. In conclusion, in this paper, we present DynamicsExplorer, a visual analytics approach to help reinforcement learning scientists to understand and to diagnose their model for robot control tasks, especially when dynamics are involved. With DynamicsExplorer, scientists can overview the behavior of their model under different parameter settings, which help them to identify abnormal cases. They can correlate the test result with the dynamics-related parameter. Besides parameters, they can also form and verify hypotheses between the dynamics and the underlying machine learning model. We also show various use cases, such as correlation between fail case and the parameter settings. We can also locate neural network channels that contribute to specific fail cases. Most importantly, with DynamicsExplorer, we can provide guidance for scientists to adjust their model. Thanks for listening. Feel free to contact us if you have any questions.